Good morning, good evening, good afternoon, good night, wherever you happen to be. Thanks for joining me. The model I want to describe today is a model that I've used for estimating fecundity in birds, looking at nests or broods of precocial offspring. I'd like to imagine that it has more flexibility than that. As far as I've gotten with exploring that flexibility is to include a cute picture of bear cubs and monarch larvae on the cover slide, though. The model is based on nest survival models, and nest survival models, probably the two important features of them, they're interval-based survival models, and we condition on when we first find a nest or first start observing a brood. We ignore whatever happened before we started monitoring the nest. That doesn't become part of the data. And if a nest or a brood survives the interval, we treat the likelihood for the survival as having survived every day of the interval. And again, these intervals can be flexible, so it might be 10 days, and the next one might be 9 days. And then the other interesting part of these models is during the final interval, if the nest or the brood happens to survive, the likelihood looks just like all the previous likelihoods. But if the nest fails, we don't know when it failed. All we know is that it didn't survive. And rather than adding up the probability that it could have failed on any one of these 7 days, that probability is just equal to 1 minus the probability of having been successful. So this is the basic structure I'm working with, but I want to add a couple of nuances. One of them is that traditionally, nest survival models have treated success as being 1 or more eggs hatched, and that's a successful nest. Now, if you're wisdom, the Laysan albatross, and you only have a single nest, single egg, well, Bernoulli would be happy with you. Success is straightforward. And but if you're a red-headed woodpecker with a clutch of 6, and you're successful, and yet you're successful by only fledging 2 out of those 6 offspring, it's kind of like getting, I don't know, a D in organic chemistry and saying you passed the class. Yes, you're successful, but you're a little less successful than wisdom. So we have this issue of partial success versus complete success that I want to consider. Also, nest survival models typically are often referred to as known fates models. The assumption is that detection's perfect, but what if it's not? Here's a brood of mallard ducklings. You can see that the female has a radio antenna. That's how we find the brood. The ducklings are unmarked, but we can all count to 6. And assuming that there are no offspring out of the image here, that's a complete brood count. This one's a little more problematic, and I've looked at this image a number of times, and I know there's at least 9 ducklings here, but I don't know that there aren't more hiding in the vegetation behind the ones that we can see. And here's an observation apparently of a female mallard with no ducklings, but we know from following radio marked individuals that they often take breaks of 1 to 2 hours per day away from their offspring. Maybe it's to explore new places, to move the brood. Maybe it's just to get away from the kids for a little while. But in either event, seeing 0 offspring doesn't necessarily mean that there are no offspring. We have issues of complete and partial detection failure that I want to consider. So these are typical data, and these are actually real data from mallard broods, Prairie, Canada. And I want to sort of showcase what the data look like and how people have treated these data in the past. Now, the first brood apparently failed, and protocol is typically to revisit the broods over a period of several days and confirm that there really are no surviving offspring. Here's an example of a brood that no offspring were seen on the second visit, and yet later on there were still 6 surviving offspring for several visits, showing that you can have complete detection failure. So the problem happens when you only have 1 count of 0 at the end of your observation history. Is this complete brood failure, or is it complete failure to detect a brood? And how can we sort that out? In the past, people might have censored this observation or censored the entire record, but that can potentially induce bias. What we want to do is try and estimate, did we see them or did they die? Similarly, we can have partial attrition. Here's a really clean record where the count goes from 10 to 7 and then from 7 to 3. Here's a less clean record where the counts go down, but then they go back up. So clearly this one involved detection failure. And then finally, we have detection failure during the second and third count, but on the 7th count, the terminal count, the count goes down. But is that detection failure or is it mortality? And how can we know? We need to jointly estimate both the detection probabilities and the survival probabilities. So what I want to try to do with this model is estimate complete loss of the entire group, partial loss, complete detection failure, and partial detection failure. So the parameters are going to be survival of the group, survival of the individuals within a group, conditional on the group surviving, detection of the group, and then detection of individuals within the group, conditional on detecting at least one member of the group. And these issues have been looked at previously, in fact, quite a while ago. We could address the issue of complete detection failure and complete loss using robust design occupancy models that were published in 2003. Paul Lukács dealt with the issue of partial losses and partial detection failures with a modification of the Cormack-Jelly-Sieber model. This was published in 2004. We can deal with partial and total survival losses, partial and total detection failures. And so what I want to emphasize, I'm doing nothing new here. I'm taking pieces that other individuals have already developed, but I'm putting them all together and putting them all in one piece, one model to rule them all, one model to bind them. So whether or not the brood survives is a Bernoulli probability, and we can model survival of the group. And conditional on survival of the group, we can model survival of individuals within the group. So this is part of the model. This is the part we care about the most, probably. And then we want to deal with detection in the same sort of way. We can model, do we see any member of the group and therefore know that somebody is still alive? That can be a Bernoulli probability. This looks just like an occupancy model. And then given that we see at least one member of the brood or one egg in the nest, how many individuals do we see? And again, this looks like an occupancy model with the exception that we have a count of n individuals that we're looking for. And so these are the pieces that we put together. And for an empirical test of these data, I'm using a really sweet data set based on over 5,000 mallard ducklings from 800 some broods. And I know the initial brood size from leaving the nest from nest monitoring data, and broods were counted anywhere from 1 to 20 times after leaving the nest. The females were radio marked, but the ducklings weren't. And these are the estimates of daily survival probability. It increases with age. It increases with age for the entire brood up here in blue. Survival is much lower for individual ducklings and salmon, I guess that is. And combined survival is the product of those two survival probabilities. And we get reasonably precise estimates of survival using this model. And we can partition that survival into complete loss of the entire group or partial losses within a group. Detection probability also increases with age. We have a much higher probability of seeing at least one member of the group, but when they're very young, they're hard to see. And so sometimes we have complete detection failures of everybody in the group, especially when they're young. And I want to go back to those two problematic broods. If we have several observations where we see nothing, then we're really certain from the posterior that nobody survived. But if we only have a single observation, We're pretty uncertain about what happened. They could have all died or they could have been missed. Ditto for partial brood sizes. If we have a unambiguous final count, we have an unambiguous prediction. But if we only have one count to confirm it, there's a lot of uncertainty about what's left. We can attach covariates to this model, looking at things like habitat use. And so I think the model has a lot of utility. There are a few things I'd still like to do with it. I've treated complete losses as an all or nothing thing using zero inflation. I needn't be completely independent or all or nothing. A beta binomial might make sense. I'd like to do some more simulations to assess the reliability of this model, but it seems to work well. I really need to get it published and out there, and I should stop now and take any questions.